In this video, I want to demonstrate how to carry out independent samples t-test in HAB. So here are the steps to follow in conducting independent samples t-test in HAB. So the first step is to, as usual, to estimate the descriptive summary of the variable. That is optional anyway. So the second step is to test for normality of the dependent variable in each of the independent groups. Okay, so that is across each of the independent groups. So we also have step 3, that is test for variance homogeneity. That's another assumption. So the assumption of normality must be met. Likewise, the assumption of the homogeneity of variances must be met. So that's why it's very important we test for this. Then if these two assumptions are met, so we proceed to conducting the independent t-test. Then if the test is significant, so we can now estimate our effect size. So now let's go. The non-hypothesis we have at hand is that we want to test if there is significant difference in weights between gender. So we have male and female, and their weights have been measured. So we want to check if the average weight of male is not significantly different from the average weight of female. That's what we're trying to test. And data set we are going to use is gender weight. I've already set my open directory. Now I will continue by importing my data set, and I'm assigning this to this variable, that is gender weight underscore df. Show you the data frame. Now let me import data set. You can see it has appeared in my environment, telling me that I have 40 observations of 3 variables. 40 observations of 3 variables. So I may want to view my data set. So I will use the function view, then the argument will be this, the name I've assigned my data set to. If I run this code, I just place my cursor anywhere on this line where I have this code, anywhere. So I run that, my data set will come. You can see it has come up. So I have gender, and then I have weight. Okay, gender and I have weight. You can see. Then going back to my house script. Then for convenience, so let's attach our data set to bypass $sign. So attach that, so it has been attached. Then the packages I've been using, let me load them once and for all. So I've loaded all of them. Then now let me start. Step 1 says I should estimate descriptive statistics. So I'm going to use, because it is this we have a grouping variable and we have the dependent variable. So what I'm going to do is that I'm not going to estimate descriptive statistics on the dependent variable alone, but I want to estimate descriptive statistics across the gender. So for male, I want the statistics for male weight and for female weight separately. So I'm going to use describe by function instead of describe. I'll be using describe by. Then the first argument, these functions are available in psych package. So the first argument will be the name of the dependent variable, that is weight I have. Then the grouping variable, that is gender. You can see weight, gender is the grouping variable. So that's what I'm going to put comma grouping variable. Okay. Then I run this code. If I run this code, I'm going to have my result. You can see group for F, that is for female. I have mean, the average mean is this, standard deviation, you can see maximum or minimum, another information. Then I have for mean, then standard deviation for male. I have minimum weight for male, maximum weight for male. You can see another information. Okay, I may want to check if we have there are outliers. Okay, there are outliers, so I can use box plot to check for outliers. Okay, I can use box plot to check for outliers. So I'm going to use the function box plot. Then I'm going to put my dependent variable. First, I'm going to run it on gender, then main. Then main, that is the main stand for the title I want to come with the title I want my diagram to come with. That's box plot of weight by gender. So if I run this, I'm going to have that. You can see I have this. So let me zoom it. Let me zoom in so that if you come clearly, you can see I have weight by gender. You can see for female, for male. If you look at it, the box plot can also tell you something else. Look at it. We have 1 point here. This is an outlier here. Then we have an outlier and female group. Anyway, another thing that box plots tells us is that we can check, we can be able to see if the variances are equal. We can see if variances are equal. You can look at the spread. Look at the spread of this box plot. You can see they are not likely to be equal. The variances are not likely to be equal. You can see that. Okay. Now let's check, but we are here to conclude. But we are the main purpose of drawing these box plots to check if we have outliers. Anyway, so now let's go to the next step. That is normality test. Normality test. So and we are going to use the function ggqqplot to do that. So in this function, because we want qqplot for each of the group, so we are going to we have additional information. So the first argument will be the name of the data set. Okay, that's gender weight df. Gender weight df. You can see gender weight. That is the first argument there. Then followed by the name of the dependent variable. The dependent variable, that is weight. Then we have comma. Then we have facet.by, that is the grouping variable. So we write the name of the grouping variable. Then we run this code. If I run this code, I'm going to have qqplots for each of these groups. So you can see for both groups, you can see for both groups here, we seem to have normally distributed data. That is, weight is normally distributed within each of these groups, mean that they are close to this line, this straight line, this theoretical line. Likewise for this one. So we can see that these weight, the variable weight is normally distributed within each of these groups. Okay. Now let's see the behavior by using formal test. Okay. If we use formal test, let's see what will happen. The formal test, the term we are going to use Shapiro test. Because we are grouping it, we are going to use the function by function. Then the first argument is going to be the dependent variable, second argument is the grouping variable. Then the last one is going to be the name of the test, that is Shapiro test. Then if I run this, I'm going to have my result. For each of these, that's for female, you can see 0.2 is greater than 0.05. So we cannot reject the non-hypothesis of normality. So we assume that within female gender, weight is normally distributed. Also within male, look at this, 0.99886 is greater than 0.05. So you cannot reject the non-hypothesis. So we also assume, you can also conclude that the weights are normally distributed within male gender. You can see. So we arrive at the same conclusion when we use visual inspection, that is qqplot. So we are the assumption 1 has been met. So let's test the assumption 2. That's homogeneity of variances. So we are going to use two approaches. The first one will be the rule of thumb by comparing the standard deviations of the two groups. Okay, if the standard deviation of one group is not more than twice of the other, okay, So we are going to assume homogeneity of variances. Otherwise, no homogeneity of variances. Now, the function we are going to use is called aggregate. It's an R-based function, aggregate. Then the first argument will be the name of the data set. The name of the data set, that will be the first argument we are going to use. So you can see the name of the data set here we use here is gender weight. Okay, I think something is missing here. Gender weight. Where is it? But I put DF here. So that's why I just copied it. I want to correct that now. Okay. So now gender weight, that's the name of the data set. Then weight, I'm going to run weight on gender, the dependent variable first, then on the grouping variable. Then I'm going to command the name of the statistic I want to use, that is SD, that's standard deviation. So let me run that now. So you can see the standard deviation for female is 2 points, it's about 2.03, and that of male is about 4.4. You can see that 4.4 is more than twice the twice 2.03. That is the standard deviation. That is the standard deviation of weight for male is more than twice the standard deviation of female. So here we cannot assume homogeneity of variances here. We cannot assume that variances are equal given this rule of thumb. But in order to be confident of our conclusion, so let's use formal test. That's Levin test. Let's use Levin test. Okay, Levin's test. Using Levin test, we are going to use the function Levin underscore test. This function is available in one of the packages we've loaded earlier. That is our status function. Look at this, our status function is available there. This Levin test. So the first argument is going to have is the name of the data set. Okay, then we are going to have weight. So we run weight on gender. So this factor we put here is to check out that this gender is a grouping variable. It is a grouping variable. Then comma, we have center. We have center equal to mean. Okay, we are centering it around the mean. So now let's run Levin test. Because this is Levin test. We have the p-value when less than 0.05. So we reject the null hypothesis of variance homogeneity. You can see, therefore, variances are not equal. Now we can see that we arrive at the same conclusion when we use the rule of thumb. Okay, that the standard deviation of the weight of male is greater than standard deviation of the weight of female. Okay, so this test also supports that the variances are not equal. So if variances are not equal, so we are going to use a special case of independent sample t-test. So we call it wedge test. Wedge test. That's what we are going to use. So the only difference between wedge test and independent sample t-test, okay, is just that wedge is a special case of independent sample t-test when that is used when variances are not equal, when the assumption of variance homogeneity is not satisfied. So what we are going to do is just to set our option var dot equal to false here, telling out that our variances are not equal here. That's what we are going to do. If variances are equal, this var dot equal is going to be set to true. It's going to be true here. So now let's run the test. So this t-test function, t underscore test function here is available in our statics function. We've already loaded that package. Okay, so the arguments that we are going to put in this function, the first argument is going to be the name of the data set. Okay, that is our data frame. Then we are going to run the dependent variable on the grouping variable. Then we are going to set var dot equal to false, that variances are not equal. Then we run that. So if you run that, we have our results here. We have our results here. We have our statistic here. Then the p-value. We have the p-value here. Statistic here. We have the p-value. Less than the conventional level of significance. That's that is 0.05. So we reject null hypothesis that there is no significant difference in weight between gender. Okay, you can see when we conducted our descriptive statistics, you can see that the mean for female, you can see mean for female is 63.5 and the mean for male is 85.83. So what we are trying to check is whether the difference between the mean weight is significant statistically or not. But the results of these two tests are shown that it is the difference is statistically significant. So we get one hypothesis that the mean weight is stable. So having found a significant result, so we can proceed to estimate our effect size. So by using our usual OND effect size test. So we have the same argument, the name of the data set, then we run the dependent variable and the equivalent variable. We are going to tell that the variances are not equal. So now we can see the interpretation here, the magnitude is large, this effect size is large.